Hello, pre-calc. So this is 6-6. This is kind of a heavy-duty section. So this video might be a little long. You might want to break it up and watch a page at a time. But we're going to first talk about inverse functions. And by that I actually mean a function in the true sense of the word, a function that passes the vertical line test and is a function. So our inverse functions, remember when you're finding an inverse, you switch the x and the y. So what that means on a coordinate graph is we are going to switch the y and the x axis. So for the inverse sign, what you would see is instead of going from -1 to 1 on the y-axis, which is usually the high and the low, that's going to go on the x-axis. And the inverse sign, if I were to then graph it, I'm going to kind of put some labels up here, and I'm going to do it as a circular function with our radian measures. And I'll put pi up here. And so if I were to actually graph the inverse sign, we know that the sine of pi over 2 is 1. We know that the sine of negative pi over 2, which is the same thing as 270, is -1, and we know sine is 0. So the inverse graph would look like this. Now, that keeps it a function because if it kept going, the graph would continue like this. So what we have is a particular limited domain and range where x will stay between -1 and 1, and the range will be between -pi over 2 and pi over 2. That keeps it as a function. And this is going to be where we have what's going to be called the principal branch. This is going to be a huge concept in this section. So realize from -pi over 2 to 0, I call that the pre-first quadrant. So when you're taking an inverse function and its negative value, you're always going to pull it from the pre-first quadrant. A little more of that later. Let's look at your inverse cosine. So same labeling. Here's -1, here's 1, here's pi over 2, and pi. We could do -pi over 2, -pi. So we know that, let's see, at pi over 2, cosine is 0. At 0, cosine is 1, because remember it starts high. And then at pi, cosine is -1. So the principal branch would look like this, but the reality is that that graph would keep going, but then it's not a function because it starts to go over on itself. And you can kind of see, if you look at the graph sideways, then you start to see a little more. And we're going to do a little activity in class with patty paper to show how to figure out these. But you can also just switch your x and your y and figure it out that way. So this will also be -1 to 1, and the range for the cosine is going to be between 0 and pi in order to keep it as a function. So that's going to cover the first and the second quadrant, from 0 to pi over 2 and pi over 2 to pi. Then lastly, we have our inverse tan. Now the inverse tan is a little bit of a different ball game because remember, it doesn't have a max and a min, but it does have the asymptotes. Whoops, that's a positive pi over 2 right there. This is a -pi over 2. And the graph, so here's your asymptotes. That would be on a normal inverse tan graph. And if I were to graph it, we know that it will be negative. It's going to be 0 here, and then again, pi over 4, your graph is at 1. So we're kind of hitting the points we know. This is going to be your inverse tan graph. So it will stay a function. So its domain is going to be all real numbers. But the range, and this is important, notice that open brackets, because these are asymptotes, from negative pi over 2 to pi over 2. All right, so what I'm showing you here are what are called principal branches, which affects when we go to evaluate an inverse trig. Because think about it, if I do the inverse sine of, say, pi over 6, no, that wouldn't be, the inverse sine of 1/2. It's like, okay, so it's positive. Do I want 30 degrees or do I want 150 degrees? So your calculator has to make a decision because there's two values, and it chooses from the principal branch. Here's a little diagram that I use to illustrate this. So you have quadrant 1, quadrant 2, quadrant 3, quadrant 4. So if it's a sine, and actually, it's not quadrant 4, I call this the pre-quadrant 1, because this is going to be negative pi over 2 to pi over 2. And so if it is, everyone that's positive comes from the first quadrant if you're taking an inverse trig. But if it's a negative ratio, your inverse sine and your inverse tan are going to come from the pre-first quadrant, as well as the inverse cosecant. And then you have from 0 to pi, I'm going to do that like this. So again, all the positive would come from the first quadrant, but if it's negative, then you're going to have your inverse cosine comes from the second quadrant, as does the inverse secant and inverse cotan. That one's a little bit of a, because of where the asymptotes fall. All right, so this kind of tells us, and notice that no one comes from the third quadrant. So you have or the fourth quadrant for that matter. It's the pre-first quadrant, negative pi over 2 to 0, or 0 to pi over 2. This will make more sense as we keep going. So let's talk a little more about this. We have the inverse cosine function, that is what you know, you are familiar with, versus the arc cosine relation. Inverse cosine is a single value. So for instance, if I go to my calculator and I say, what is the inverse cosine of 1/2? I'm only going to have one answer that comes from the positive first quadrant. But as you can see from the graph keeps going and going and going. And we know even within the unit circle, there's two places where arc cosine might be positive. So arc cosine, right here, it's a relation, and it covers all the arcs or angles whose cosine is a given number. The actual formal definition is right here. And so it includes, notice that embedded is the inverse cosine, and then as you go around the circle, you will have more values. So the function is the principal value, because that's coming from that limited portion. So for cosine, the limited portion is from 0 to pi, even though the function itself keeps going. So this represents the first quadrant, and this represents, oops, I should have crossed at pi over 2, sorry. That would represent the second quadrant, where you would pull your values from. All right, let's take a look at an example. Maybe that'll help with this. So we want to find the first 5 positive values of arc cosine 0.9. Let's give ourselves our cosine graph. So remember, cosine goes from -1 to 1. We have 0. We're going to go out to 2 pi. Here's pi, pi pi over 2, 3 pi over 2. So again, cosine starts high, sinusoidal, low, sinusoidal, high. So here is your regular cosine graph, which would actually keep going. So I might actually extend this. I might not do all 5. Maybe we'll have time. This would go out to 4 pi, so this would be 3 pi, and then we'll label these later. All right, so it wants us to find the first 5 positive values of arc cosine 0.9. So 0.9 is about here. So as I look through the positive one, right here, 1, 2, 3, let's make it easy on ourselves. Let's do the first 4, because that's all I have space for here. 1, 2, 3, 4. I could come back down and do it again. It's all good. All right. So how do I find this? Well, you start off with, you're going to go to your calculator, and the arc cosine of 0.9 is going to be plus or minus the inverse cosine of 0.9 plus 2 pi n. That's the definition. All right, so on our calculator, this gives us plus or minus 0.451 plus 2 pi n, multiples of 2 pi. So I'm going to start to fill in our little table. We have when n is 0, so when I let n be 0 here, whoops, I just moved everything. We just have positive, hello, why is it not writing? I lost my pen. Here's 0.451 and negative 0.451. And then what's going to happen is when n is 1, we're adding 2 pi. And again, 2 pi is like 3.14, 6.28. So you're adding 6.28 each time, really. All right, so when we fill this in, 0.451, I would add 6.28. That's going to give me 6.734. Add another 6.28 gives me 13.017. And I'll just go ahead and carry it out here, 301. Down below, I have negative 0.451. Then I'm also adding 6.282, and that's going to give me 5.832. Add it again, 12.115, and 18.399. I kind of went beyond what I needed. We want the first, well, in the table, I can get the first 5 positive. So here's the first positive. Here's the second one, the third one, the fourth one, and the fifth one. And so when I look at my graph, this one right here would correspond to 0.451. This one right here is going to correspond to 5.832. This one corresponds to 6.734. This one would be the 12.115. And if I had kept drawing my graph to get all 5, I would have crossed here, and that one would be your 13.017. So you're solving the equation, and it's like saying, okay, the tide comes in, the tide goes out, the maximum distance, we're going to say amplitude is still 1. We're not going to worry about the real world there, but let's say we wanted to know at what times during the day is the tide 0.9 feet high or something. I don't know, I'm just trying to make up something. And these would correspond to all those various times. So then the x-axis would actually be time, and this would say be distance. Okay. So the idea here is you're having to take your inverse cosine, which is a function, and look at it as a relation, which is going to have multiple occurrences as a periodic function. Okay, let's put all this together. And you're like, put what together? I have no idea. All right, so what we're gonna do is, here we have a graph, and they want us to estimate where y equals 5 intersects with this equation. All right, so you can see all these points where y equals 5 intersects this periodic function, this circular function. Those are the values we want to come up with. So in order to do that, I'm not going to estimate the x values because we're going to actually figure out what they are, but they should all coordinate with what I'm marking on the x-axis. All right, so we're going to need an equation for this sinusoidal. So notice that my high here is at 16, my low is at 2. That's a distance of 18, so half of that would put me at 9. So I know that my vertical shift is going to be 9. I can see that my amplitude then is 7. And if I do it as a positive cosine, I'm going from 4, a high of 4 to a high at 17. So the period is 13, which means my b value will be 2 pi over 13. And my phase shift is I'm starting at 4. So my equation that I'm working with is y equals 9 plus 7 cosine 2 pi over 13 x minus 4. And we're trying to see where that intersects with the line y equals 5. So what we're actually going to be doing is setting 5 equal to this equation. Most of this is going to be algebra, but at some point we have to take the inverse cosine, and that's when we start doing what we did on the previous page. All right, so let's start our algebra at least. We're trying to isolate x, so we have a lot of layers to peel away. So the first thing we're going to do is subtract 9. So that is going to give me -4 equals 7 cosine. And when you do enough of these, there will be some shortcuts you can take, but to start off with, I'm going to take it really slow. All right, so this next step, we're going to divide by 7. So I've got -4/7 equals cosine 2 pi over 13 x minus 4. All right, at this point, how do I separate cosine from its argument? This is where you have to do, and we don't want to just do one value because we're looking for multiple values. So I'm taking the arc cosine, which is basically the same thing as inverse cosine, the arc cosine of both sides, because that's going to cancel that out. And then remember, by definition, the arc cosine of -4/7 is going to be plus or minus the inverse cosine of -4/7 plus 2 pi n, and that's all going to equal your 2 pi over 13 x minus 4. To be perfectly honest, I don't usually write all of that. I usually just write the plus or minus. Well, it's not a bad idea to do it. Okay, so now we go to our handy dandy calculadora. And this now, because we're using the calculator right now, you need to understand where is it getting its answer from. So this is a negative ratio. Cosine is negative in the second and third quadrant, but remember, we only want that one value. So it's going to pull from the second quadrant, but that's what the plus or minus does. So it's pulling from the second and the third quadrant for this, because we want the relation, not the function. So plus or minus 2.179 plus 2 pi n equals our 2 pi over 13 x minus 4. All right, that's really the only trig in this. Okay, knowing to write it as plus or minus 2.179 plus 2 pi n. Right now we're only doing cosine, which is a little easier, so that's kind of nice. We still have to isolate our x value. All right, so what I'm going to do now is I am going to put my equal sign a little bit closer here because I'm going to multiply by the reciprocal, both sides, 13 over 2 pi. So put parentheses around this, 13 over 2 pi, because that has to distribute to both terms in that parenthesis. So it will cancel over here, so all I have is x minus 4. On this other side, I have plus or minus, so 2.179 times 13 divided by 2 pi. Please, when you do your division, put that 2 pi in parentheses. Otherwise, all you're doing is dividing by 2 and multiplying by pi. So make sure you put that in parentheses. So when you do that, you should get 4.508. We still have the plus or minus. Now this is where the magic happens. When I multiply it against the next term, notice I get plus 13n. You should always get your regular period back because the period is 13, and there's that. Okay, so we still haven't completely isolated x. At this point, we are going to then add 4. So I'm adding 4. But remember, it's 4 plus and 4 minus. So I have 4 plus 4.508 plus 13n, and I have 4 minus 4.508 plus 13n. Those both are going to equal x. So what we call our general solution, because it has an n involved, is going to be x equals, so this will be 8.508 plus 13 times n, or negative 0.508, because 4 minus the 4.508 plus 13n, multiples of 13, because that's the period every time you go around again. All right, so what did we want? We wanted the first 6 values. Positive values, I guess, is what we were after. Okay, so when n is 0, that's the n we're talking about. We're going to fill in. I like to do it as a table. You don't have to. The book doesn't do it that way, but that's just me. All right, so if I put it into this table, when n is 0, I have my, I'm going to do smallest to largest. So I have my negative 0.508. And I have my 8.508. And then what I'm doing basically is I'm adding 13 each time. When n is 1, that's 13. When n is 2, that's like adding another 13 or 26. So I just add 13 to the previous, and I like to just fill out the row. So 13 minus 0.508, that's going to give me 12.492, add another 13, 25.492, add another 13, 38.492, and then going down to the next row, adding 13, I get 21.492, add 13, 34.492, and if I added another 13, I'd have 47.492. All right, so if we look at our, and these are called particular solutions, because they are the exact point where the line y equals 5 intersects our original graph. So I'm not going to find all of them. This was our negative 0.508, looking at our graph. Then our next value where we cross, that's going to be the 8.508, which makes sense, a little bit before 10. Then this one is going to be our 12.508. So you can see these are the values that we algebraically came up with. Yeah, I'm not going to go ahead and put all of them on here, but you can kind of get the idea. All right, so the whole principal branch kind of conversation came in it sort of lost a little bit of the meaning because we're using the calculator to do it, but that came in here where we were taking the inverse cosine to get the general value. And the calculator understands that if it's a negative ratio, it's pulling it from the second and the third quadrant because we want the relation, not the function. Now, what if we take the calculator away from you? Because that happens. So here it says, solve algebraically. Find the first 4 positive values for x. All right, so we start off algebraically and we divide by 2, divide by 2. So I have negative rad 3 over 2 equals cosine 2x minus pi over 2. All right, at this point, we take the arc cosine of both sides. I tend to just write inverse cosine, but I'm afraid that I guess I should emphasize what we're really doing. We're taking the arc cosine of negative rad 3 over 2. And again, when you take the arc cosine of both sides, these are going to cancel, but I'll just show what I'm doing. Okay. And remember, the definition of this is plus or minus the value of arc cosine, which is, here I'm going to write it out again, inverse cosine, negative rad 3 over 2 plus 2 pi n, and that equals now our 2x minus pi over 2. All right, so we have to do some evaluating. So this is a negative ratio. Cosine is negative in the second and the third quadrant, and rad 3 over 2 is going to happen at, I'm having to convert to radians in my head, 5 pi over 6 and 7 pi over 6. So it happens at 150 and 210. So this turns into plus or minus 5 pi over 6, because you notice I went plus 5 pi over 6, negative 5 pi over 6. So cosine's very friendly that way. When we get into sine, it won't be, unfortunately, as friendly. So this is going to then equal 2 times x minus pi over 2. I'm going to ignore all this stuff for a minute because it's in the way. So we have to still solve for x. So I'm going to multiply everything by a half. And I'm going to continue down below. So this is going to give me plus or minus 5 pi over 12 plus pi n equals x minus pi over 2. And then our last step is to add pi over 2. Add pi over 2 to both sides. So again, this breaks up into pi over 2 plus 5 pi over 12 plus pi n, and pi over 2 minus 5 pi over 12 plus pi n. All of that is going to equal x. So we want to put it together. Do not ever give me an answer like that. You do the addition. So I need a common denominator, so this would be like 6 pi over 12, 6 pi over 12. So my general solution, 6 plus 5 is 11 pi over 12 plus pi n, and pi over 12 plus pi n. That would be your general solution. And they wanted, again, the first 4 positive values. So my table's way up there, so I'm just going to redo my table down here. So I always like to start with when n is 0, that's going to be pi over 12 and 11 pi over 12. And when I add n equals 1, it's like you're just adding pi. But since we want a common denominator, you're really adding 12 pi over 12 so that we have the same denominator. All right, that's the same thing as just adding pi to each time. So this will become 13 pi over 12. This one will become, we're adding 12, so that's 23 pi over 12. And what did it want? It wanted the first 4 positive values, so at that point, I've got 4 positive values here. So what you would do, don't leave it in the table, my particular solution, and it's nice, you should always write them in order, so it's going to be pi over 12, 11 pi over 12, 13 pi over 12, and 23 pi over 12. And those would be my first 4 positive values without touching a calculator. So it is possible to do these without. So you do need to know your trig, in a sense, your inverse trig. And yeah, that should be it.